In this video series, I'm going to be touching on 2gen for the 4x4. Specifically, I will be concentrating on what I usually concentrate on in these type of videos, and that's 2-cycle odd parity algorithms. There are actually 5 different move sets of 2gen on the 4x4, which allow you to create a single dedge flip, in other words, where it's possible to do that, and that are the following 5. I'm going to be using old WCA notation where lowercase means inner slice, so lowercase r means inner slice. So the first type is lowercase r and uppercase U. The second is lowercase as well, but a triple layer turn of UW. And then the same thing, but of double. And then I'm going to be using a wide of r and upper. And then the last one is a wide and then a triple. Woo! Now, I'm making a series about this because I have quite a bit to say about several of these, not all of them. The last one and the third one, I don't have too much to say about them because I'm to be honest, I'm quite clueless about them in general. But I do find a single dedge flip algorithm in those videos, so those are rather short. But the other ones are quite detailed that I think it would be too much to put into one video. With the exception of the last one, Ben Whitmore has used his KSolve++ program, and Bruce Norskog and Lucas Guerin have used KSolve to find the move optimal sequences to all of the previous 4, but like I'm saying, with the exception of the last one, we know what the move optimal move sequences are for single dedge flip algorithms in all of these move sets, but not in this one yet. And to see what they are, if we go to the 4x4 Parity Algorithms page at Speed Solving Wiki, I have a 2gen section on parity algorithms. And I'm going to go just by half turns as opposed to quarter turns like I usually do. I'll call this type 1, type 2, type 3, type 4, type 5. So for type 1, move optimal is 22. In the video dedicated to type 1, I'm going to first derive a 41 move algorithm, and then I will finish off with a 35. And every single one of these videos is talking about human solutions because we already know what the move optimal solutions are. So we're just trying to find a move sequence that we can understand and make sense of. And then from that point on, over time, if we experiment enough and as we accumulate our knowledge, then we'll find shorter move sequences ourselves that are understandable to us, and if we explain well enough to others, they can understand it as well. And that's what I'm hoping to do in this series, is try to make sense of the algorithms that I did find by hand. And I do mention when I say that it was unobvious or I experimented or things like that. I will say that, I promise. And I'll probably explain too much rather than too little. For type 2, the move optimal is 29 moves. And in the video that I dedicate to that, I'm going to first derive a 44 and then a 37. So that's very, very close to optimal. For type 3, the move optimal is 29. I'm going to derive just one. It's going to be 61 moves long. Not very proud of that. Pretty much double the moves, but anyway. For type 4, the move optimal for the 4x4, Ben found one for the 5x5 as well. I'll get to that in a second. But for the 4x4, Bruce Norskog and Ben independently found that the move optimal sequence to flip a dedge on the 4x4 in this move set, very strict move set, may I add, is 26 moves. In the video dedicated to that, I'm going to derive a 69 first and then a 57. We can see that the optimal algorithm for the 5x5 is actually longer than it is for the 4x4. This is a rare occurrence with parity algorithms in general. Usually the 4x4 and 5x5 are pretty much the same number of moves. You can have a direct 4x4 translation to the n by n, or pretty close to it. Might be just a couple moves more, but this is 7 moves difference. I'm going to derive one myself for the 5x5 in this move set, which is going to be 177. So 57 to all of a sudden 177. But it's easy to understand. I technically did find a 163, not that much shorter, and I probably could find a shorter one, but that one is very straightforward and I want to let y'all explore. For the last move set, and the move set for RW3UW, which is not even on here because Ben didn't find, I believe he's currently looking for one, but he hasn't found one yet, so the move optimal algorithm is unknown. But I'm going to find one that is, well, I don't even want to say how many moves it is. I'll just say it's hundreds of moves. It's quite long, but it's very easy to understand. So that will be the last video in this series. And lastly, may I mention that for type 4, I'm going to find a move sequence using U and RW turns alone to find a move sequence which does the move R2. And I'm also going to find a move sequence which does the move R. Those are big challenges within themselves. But after I break it into that move set by finding a single dedge flip algorithm for the 4x4, then we'll have enough of a foundation to actually do such a thing on the 4x4 in that strict move set.